Now, was it you, Mr. Hurst, that gave me the idea that the radius of a sphere has to be positive? It can't be 0. Is that the one? Are you the one that mentioned that yesterday? Okay. I thought more about what you said, you know. I was kind of like, I kind of like that. You know, I like that whole idea of, you know, why would we include 0? Yeah, so I think that better implied domain there, or relevant domain for that sphere, probably is what you were suggesting. I would have to agree. Okay, I kind of like that. So, you know, I thought through that, because you're kind of right. I mean, like a dot. I mean, come on. You know, I mean, we could say the sphere has a volume of 0, but how dumb is that? Anyway, I mean, what kind of balloon would that be? Seriously. Okay, so we talked about these 2 facts which you really need to understand. What do we know about everything under a radical? Everything under a radical has to be what? Greater than or equal to 0. Okay? Then we also talked about denominators. What do we know about every denominator in the universe? And is it what? Can't be 0, thank you very much. Can't be 0. Those are the 2 major facts that we need to know. Now, those aren't the only restrictions in the universe. I mean, we have restrictions on logarithms. We can talk about those. But these are some common ones that we need to focus on for now. And you guys walked me through the first one, letter A there. The x plus 3 had to be greater than or equal to 0, which means that x has to be greater than or equal to negative 3. And we wrote the domain of that as bracket negative 3 to infinity. Okay? And then we got to this next one, and we talked about the 2 individual pieces. The numerator had x is greater than or equal to 0. The denominator had x minus 5 does not equal 0, which resulted in x not being equal to 5. But we never got a chance to put those things together. So we need to do that. You have about 30 seconds to talk to your neighbor and figure out what you think the domain is for those putting those 2 pieces of information together. Okay, so what's this domain? What's the smallest thing that you can think of for x out of the information you've been given? We know that it has to be greater than or equal to 0, so 0 would be the first thing that we would start with. Okay? So we have everything starting at 0, going to infinity, except what? 5. So how in the world do I go from 0? Skip over 5. And keep going. That's what I've got to do here. All right, Mr. Fields, what you got? Yeah, nice job. We took that 0 to infinity, and we put a break in it, right in the middle. Grab your graphing calculator, and let's see if we can graph this thing. First of all, I want to make note that if you have one of the plots turned on at the top, like this, and then you go to try to type in an equation, you're going to be a very frustrated person because it won't graph. It's struggling to understand where you want it to graph and what you want it to do. So make sure none of those, I call them evil plots, are turned on because they would frustrate you. Now, for those of you with an old style calculator, you know, you're going to have something like this. You know what? Maybe I should just grab an old style that way. There's perfect. Do this side by side. Yeah. All right. Y equals. So those of you with the old style are going to have to do something like this. I noticed that there were a few people in a previous class, not to name names, that forgot that parenthesis right there. And so they got the wrong answer. But if you're doing with this the old-fashioned way with the older style calculator, it would look something like that. You actually have a couple choices here with the newer style calculator. So some of you are going to do something like this, and then you're going to go outside that square root function, and you're going to hit divided by parenthesis x minus 5. Now, I wouldn't choose to do it this way per se, because, and maybe you don't know this, but on the newer style calculator, right above y1, it says, for me in green, f1. All of these top keys have a function that goes with the alpha button. And if I go alpha f1, you'll notice that it has some choices on fractions, different things that are there. But the very first one right there is what I'm going to choose. When it does, it creates what looks like a vertical fraction. And so for those of you who have this, you might make yours look exactly like the one that was in the notes. You wouldn't have to use any parentheses because it takes care of that for you. So, either way. For those of you who don't have the right window, you might want to do Zoom 6, the standard window. Oops. So that we get it drawn. Now, maybe I'll bump these down a little bit so there's not so much of a shadow on them. It's getting better. There's a flaw in the older style calculator. What is the older style calculator doing with each one of those branches? It's connecting it. It thinks it's supposed to connect this branch to this branch. That's not true. You and I both know that there should be a gap right here. What number is that gap? 5, right? Because it's not in the domain of the function. But the calculator doesn't. The old style calculator had that flaw in it where it didn't know that that was not supposed to be there. And as you can tell on both pictures, it stops right there at the origin at 0, 0 because it will not go past that point. Now, I need you to be able to do something else, which we will use later on. Above the word window, so on your top row you have the white buttons there. Above the word window it says Table Setup. So please go to the Table Setup. You can change the starting position to be anything you want. Table start at 0, and according to your science class, that's the delta table or a change in the table. Right? And I have mine set to 1 although you can set it to whatever you need to, and yes, we will be changing those things in the near future. I need you to go down here and set both of these to auto. Both of them, independent and dependent variable, to auto. Right above the word graph, you see table. So we want to go to the table. Now what's interesting is it's if it's a nice value, you can see that it on the newer style calculator it changes it to a fraction. Let's make this where it won't do that on the older style. How come when I go up it says error, 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 error? Because it doesn't go back that way. Those are in the domain of the function. Well, we knew that because it started with 0. Same thing happens when you come down here to 5, right? There's no value that we can give you for 5 because it's not in the domain of the function. Okay? Let's go back and make a different type of table. Let's go down here to where it says auto for independent variable and switch that over to ask. Ask. Now when you go to your table, there's nothing in it. If there was something in it, you could clear it out or hit the delete key. What it's looking for me to do is it's looking for me to give it a value. And when I give it a value, guess what? It spits out the y value that goes with it. Don't you wish you had known about that a long time ago? I want to know what happens when you plug in 1,000,000. Guess what? This would do it pretty quickly. And the more... so I've got the rounded value in the table, but below at the bottom of the screen is the more accurate value, if you need it that far for some strange reason. You know, if you were on a game show or something like that. Okay, those two features, those two types of tables where you ask or where you create an automatic table are going to be useful to you. So don't forget about those. Table setup. Now in the near future we're going to use that auto feature quite a bit when we're looking at continuities. We may or may not get to that today. There's a lot of stuff in section 1 too. A lot of stuff. Okay. Back to our notes. What's the domain of this last one? We've got area of an equilateral triangle with side lengths of S. Obviously, we're talking about S for the domain because that's the independent variable. The area is the one that depends upon the side length chosen. So you tell me, what is a good domain for the side length of an equilateral triangle? Can you have negative numbers for side lengths of triangles? No? Okay. Could we have radical 7? Sure, but it'd be really kind of hard to measure it. But we could, I guess. What's your domain going to be? Okay, take 20 seconds to figure it out. Let's go. Talk. Talk to each other. Figure out what your neighbors think about this. What's the domain of this going to be? What do you think are the possible side lengths of an equilateral triangle? I put it right there. I know we got the whole thing. You're talking about you. Oh. All right, Mr. Hurst, what you got? All right, so we want the side length to be bigger than 0. If we had this side length of 0, we would not have a triangle. Once again, we would have a dot. Pretty uneventful.
Wait.
Yes. That's it. This is called, remember, I know the formula has an implied domain of all real numbers. You can stick any number in there you want, but the relevant domain to the situation, the only domain that matters to me for the length of a triangle. See, that there was no, I didn't have to do any calculations on that one. Why didn't I have to do any calculations? Do you see any square roots in that equation? Nope. Do you see any denominators that are variables? Do you see any denominators that are variables? Nope. So really it was just about what do you know about any side length of any triangle? Okay. Find the range of this function. You will need your calculator and you will need to graph y equals 2 over x. Unless, of course, you just know what it looks like in your head, which you probably should from last year. But, you know, it's been a little bit since you've done that. So, graph y equals 2 over x on your calculator. Y equals 2 over x. If you don't know how or you're stuck on it, please, now would be a good time to ask me. Graphing y equals 2 over x on your calculator. Now, decimals is great. I love that. No? Anybody else? Graphing on this side. We got y equals 2 over x. And which 2 quadrants are we in? For those of you who are about to ask me, which are the quadrants, we must remember how to spell the word quadrant. One, two, three, four. Of course, that's not how we spell quadrant. Okay, I'm just trying to help you guys remember. 1, 2, 3, 4. It's like a capital C, right? So which 2 quadrants are we in according to your picture? 1 and 3. 1 and 3. We got a branch here and we got a branch here. Back in Algebra 2, you talked about this as inverse variation. As x gets bigger, y gets smaller, that kind of idea. Now range, that's the idea, and I talked to you about this yesterday, this idea or this concept of taking all the points and smashing them onto the y-axis. Bring all the points to the y-axis, as if you were just mashing the graph on that y-axis. How much of that y-axis would get covered? Because that would be the range of the function. Yes, sir?
-2 to 2.
You would definitely, well, -2 to 2, most of what you just quoted is in the range, but it's a lot bigger than that. See, this thing is going up for a long way and down for a long way. So it will go way past -2 and 2, although that is in the range, or at least most of it.
Okay, talk to your neighbor. You got 30 seconds to come up with an answer on what this range is going to be. Smash it all up onto the y-axis. Okay. How much?
Yeah, the range is infinity. Because when you do the vertical, it never stops. There's no breaks. No. Because like you see,
So get 2 in. I can go over 2 and up 1. Sure. There's that'd be a 2, right? If I got, if I put in an x value of 1, yeah, there'd be a 2 in it. But that's just like one number out of a lot. How do I describe it?
I finished it. 5 minutes before lunch.
You think about it. How do I describe the entire range? Okay. We get closer? What are you thinking?
Well, mine is calculator, just
Okay. Now, what you're not seeing, okay, so let's say I make a table, and I'm going to start at 0, but I'm going to go by 0.001. Okay, roll small movements. So now I'm going to go to my table. Of course, at 0, there's an error. Okay, but at 0.01, I get 2,000. Okay, so in other words, the number of pixels on your calculator, it couldn't handle it. Okay, so when you get real close to this line right here, whoo, it's way up there. Okay, so I know it can get to at least 2,000. I bet it can go higher than that. Because if I entered a smaller x value and got it closer to the y-axis, it'd be bigger than that. Okay, if you are just looking at your picture and you think it stops, then I could show you that if I make a table, let's say, you know what? Just for fun, we'll leave it on ask. How about 0.001? Let's say I plug in an x value of 0.001. Answer, 2,000. Okay? How about I get closer to the x-axis? 0.0001. 20,000. So if you think it's stopping just because it looks like it's stopping on your calculator, it's because the pixels can't handle it. You saw on Desmos, you probably zoomed in, and you just kept zooming and it wouldn't stop, would it? Yeah, if you use Desmos, you can even get a better looking picture than you can on the graphing calculator. Okay, what do you think's happening? What's the range? Yes, Ms. Lee.
Okay, it's negative infinity, negative 2 and then bracket 2.
Oh, bracket, you said bracket. I'll tell you one thing. It's a lot warmer than I'm getting from other people. So we're getting closer. We are getting closer. We're not there yet. Okay, this is not the range, but we are getting closer. Folks, down here is negative infinity. Way up here is positive infinity. So at least she's got a right idea that we're at least getting a lot of values in there, yes? All real numbers, not true. Remember that whole when in doubt, all reals? The red pen of death? Did we talk about the red pen of death yesterday? No. Okay, well, let me introduce you. Okay, this is the red pen of death. Okay. Now, on the street, they call it RPOD, red pen of death. Okay. Now, all reals comes down hard on that one. Now, all reals is almost right. It is almost right. With one major exception. Not 0. So how do I modify what Miss Lee came up with what Miss Chalk just said? Zeros. Okay. Now that's much better because now we're closer to where we need to be. And what else? Parentheses. You cannot bracket them because if you bracket them, then you include them, and then I have to agree with you that it would be all reals, and that's not true. Now, what's interesting to me is that a lot of you forget what causes a fraction to be equal to 0. What causes any fraction to be equal to 0? Is the numerator 0? Right. That's exactly what we need. The only way you can get 0 in a fraction is if the numerator is 0. Most people think it's the denominator, but that's undefined. What do you have in the numerator of this fraction? 2. The important detail of what you just said was that it is a fixed value. Ain't no way in the world that's going to automatically change into a 0. Therefore, you will, I don't care what value, I don't care if you put in a billion, trillion, you go way out here to the right. You ain't never getting a 0 out of that fraction because of what you just said. Okay. Before I get into this, I want to see if you have any questions. Now, I did email you and ask you if you could work on 1 through 8. Some of you read email and some of you ignore it completely. Any of you that did work on 1 through 8, did you have any questions over those before we move on to the continuity issue? Determine whether the formula determines y as a function of x. Were there any of these? I'm guessing 5, 6, 7, and 8 were probably not that difficult, right? Did you have any questions on 5 through 8 using the vertical line test? Don't you use that heretical? Is that the right form of heresy? I think that's, I don't know. I don't have the right form of the word. I know you were going to say it. Don't you dare say it. Okay. But what about 1 through 4? Determine whether the formula determines y as a function. Did you graph them? Is that what you did? Because in order to graph them on a graphing calculator, you have to get them equal to y, which is nice for 1. That's kind of weird. Question 2 is kind of weird, because you'd actually have to split that up into 2 different. You'd actually have to do y1 equals x squared plus 3, and y2 equals x squared minus 3. Would that be a function? Would radical 9, yeah, you could do that. Is there a specific reason you chose radical 9? Yeah, sure. Yeah, it'd be fine with that. So what does x squared plus 3 look like? So do you remember what happens when it's outside of the shape? Is that moving up or moving down? Moving up. And I'm going to have to think about this because this is kind of a weird one I've never seen before. How about x squared minus 3? Down? Is that whole thing a function? Say it louder. No, fails. Why did I split it into 2? Is that what you mean? Or why did I shift it down also? This is kind of weird. Say it again. I drew 2 because they actually have 2 different things here. X squared plus 3 and x squared minus 3, which is kind of bizarre. I do understand. It's like they tried to combine 2 equations into one and then say, hey, is this a function? That's kind of weird. I mean, that's not normal. I will grant you that one. How about question 3? Solve that for y. Tell me the 2 things you need to do to solve that for y. What do you do first? Divide by 2. X over 2. All right, that's y squared. Then what? Take the square root, right? What do you get as a final? Y equals. Don't forget the plus and the minus. Which means when you're graphing it on a graphing calculator, you would have to split it up into 2. You'd have to have a y1 equals the positive square root of x over 2, and you'd have to have a y2 equals the negative square root of x over 2. Now, for those of you that remember, the square root of x over 2 would be, it's a scale change, and we'll talk more about that later, of a positive square root function. Looks something like that, just a basic idea. What's the negative version of that look like? It's a mirror image across the x-axis. So what do you think? Yes or no? That's a no. So you had a no there and a no there. Which makes the other 2 yes? What kind of logic is that? Seriously? No way. I mean, it just happens to be that way, but that is not, don't you dare listen to that. Okay? It's right, though. Why? All right, so what kind of shift is this? It is a right shift of 4 units, so you have an absolute value. Oops, sorry. You have a square root function that's been moved right 4. It's a positive square root, so it's the top half. Yes, it does pass the vertical line test. And this down here, can you name the only type of line that is not a function? Can you name the only type of line? Because that down there in number 4 is a linear function, right? Can you name the only type of line which is not a function? X equals 0 would classify yes as not a function. So would x equals 3, x equals 17, x equals 1,000,000, because they are all what type of line? Don't tell me straight, because all the lines are straight. I heard it. What's the only one that fails the vertical line test? A vertical line. I know, it was dumb, but yes, that's the only type of line. So, ain't no way in the world number 4 is not a function, because it's not a vertical line. Right? It doesn't fit the form x equals 5, x equals 21. It's got a y and an x. So, if you go solve that for y and graph it, I guarantee you're going to get a function. All right. We'll go back to the continuity issue. We are not going to get real far in the continuity issue before we need to stop for today, and we'll pick this up tomorrow. There's a lot of stuff in section 2 that you really need to understand, and if you don't understand it, it's going to bite you. Continuity is exactly what you think it is. Can I draw the graph without having to pick up my pencil? Can I draw the graph without having to pick up my pencil? That's a basic definition, extremely basic definition of what we call continuity. So the picture on the far left is continuous at every single value of x. I don't know why they didn't put little arrows on these, which bothers me, you know. The one you and I looked at a few seconds ago over here is called an infinite discontinuity. It breaks in the middle and it goes up forever and ever and ever. Now, do they have to go in opposite directions? Absolutely not. You guys studied one last year that did this. Y equals x, let's say like 5 over x squared. That example right there is one that has an infinite discontinuity and they both go up to positive infinity. Well, then there's one called a jump discontinuity. Do you have any idea why they call it a jump discontinuity? Because it jumps, right? You know, you're traveling along and then all of a sudden it magically just, you know, separates the graph and goes up or down, you know, dramatically. There are two types that are called removable discontinuities. This one right here is called a removable discontinuity. What do you see in that graph? Maybe I should zoom in. You see a hole. There's a missing point. How well do you think your graphing calculator is at showing you that missing point? How good of a job do you think your graphing calculator does at showing you that missing point? Do you think your graphing calculator is good or bad at showing you that? Horrible. How about Desmos.com? Do you think that's good or bad? I don't know if it does show you the removable ones. How small is a point? Remember their definition, geometry? There's no thickness. There's no width. It's kind of hard to show that. You will have to be able to do algebra to show me where that spot is. Because it's not going to magically show up on the technology that you're using. Which, I know, you want it to show up, but it doesn't. Okay, the other type of removable discontinuity that you have here, look at this one. It's got the same similar type of hole, but guess what? There is a point at that location. There is an x value. It just has a radically different y value that doesn't match everything that's close by to that hole. Those are kind of unusual. Not normal, I should say. We will continue our continuity discussion tomorrow. You can continue working on homework, although you won't get super duper far until we get more into this discontinuity idea.